In this video, we will discuss the Morse circle. Circle is a graphical tool which we use for stress transformation. So what we do in stress transformation is we know the stress components in a given orientation. Well, this is a two-dimensional example, and we like to know the components in a new x prime, y prime coordinate system. We have to transform the stresses and find the new stress components. For this, we use in two-dimensional case these two equations. So sigma x, sigma y, and tau xy is given, and theta is the angle where we are interested, so we use these formula. If you take these two formula and eliminate the angle theta, so you can get a relationship between sigma x prime and tau x prime. So the other values are known stress components from the initial orientation. So if you look at this equation is actually an equation for a circle. So if you put instead of this term a sigma average, and if you call this term R, so you see this is a x minus a squared y squared plus r squared. This is the equation for a circle. For my circle, well, the center is the average stress, and the R value, radius, can be calculated with the help of the stress components. Now I have the equation of the circle. I have calculated the center and the radius. So I put the center and taking the radius, I can draw my Morse circle. So how did I draw this circle? I used the components for a given orientation to find its center and its radius. So each point on this circle is satisfying this equation. That means it represents a plane. For example, this is a plane, and let's take the plane A. This plane A, it has sigma x and tau xy, so you can take sigma x and tau xy as your components, and what you do is draw the point, and this point A represents your plane. So please note that the tau positive shear is downwards in the Morse circle, and positive sigma is to the right. So we know that in the Morse circle, each point corresponds to the stress components on a certain plane. Let's take this plane, A, and let's take this point A, which is the point representing my plane. So I'm interested in the stress components on another plane, which has an angle theta. So what should I do? I have to rotate my A to the point which, let's call this plane D, which represents the plane as point D. So you see the angle I have to rotate is 2 theta if the rotation on the element, on the stress element is theta, I have to rotate by 2 theta on the circle, and starting from point A and rotating by 2 theta, I reach point D, and point D has the stress components which I am looking for. It has the new sigma x1 and tau x1, y1. You see, the new components are sigma x1, tau x1, y1. So this is how you use the Morse circle for stress transformation. Okay, let us draw our Morse circle for a given element. So the first thing I do is to draw the axis sigma and tau, positive tau, it's downwards. Then the points A and B, which are on this element, it has its sigma and tau components. Let's take this point A and this one point B. While point A has the component sigma x and tau xy. And as you see, between planes A and B, well, the angle is 90 degrees. It corresponds to 2 theta, which is 180 degrees on the Moore circle. So when you draw the line between these 2 points, so it will cut this center, and the angle between A and B will be 180. So it means that you can easily draw the Moore circle like this. Clearly, point A, point B, its coordinates as you see, and you connect A and B line and find the center. Another possibility to draw the Moore circle is to use mathematics. Calculate the average, calculate the radius, find the center, put the radius, and draw the circle. You can of course check whether the points A and B are on the circle or not. Well, using the Morse circle, we can do stress transformation. So we have learned that point A represents my plane A. So I can take this as a reference point, well, where you call it theta equals to 0. So when you want to make a transformation by theta and come to a new plane D, so what you should do is move by 2 theta on the Moore circle and reach a new point, which is representing the plane D, and the components will be sigma x1 and tau x1 y1. Okay, so point E, which is perpendicular opposite to D, so it is located at 180 degrees, so this will be your point E. So in summary, when you rotate the element by angle theta, the point on the Moore circle moves by an angle of 2 theta. So this is everything more clearly. Point A and B are the planes on this element. So after rotation by 2 theta, you come to a new plane which is at an angle theta, and the new coordinates can be easily determined with the help of the Moore circle. Let us discuss how principal stresses in the Moore circle are represented. Well, we know that these are minimum and maximum stresses, and on the principal surfaces, no shear stress components are active. So you can find these sigma 1, sigma 2 points very easily. These are on the axis of the circle as sigma 1 and sigma 2, and you can also find the orientation of these planes. So if this is your reference point A, so well, it lies on principal on the Morse circle by 2 theta. So on the actual element, the angle will be theta, and this will be your new direction, and this will be your new plane. So you can also determine the maximum shear stresses with the help of the Morse circle. The maximum is here, minimum is here. So because positive tau is downwards, so the values of the tau max value is r. That's the radius of the Morse circle. So you can find also the orientation, for example, of the maximum shear stress from your reference plane, that is this plane. So you move by 2 theta and get to the maximum point. And here, when you determine 2 theta on the Morse circle, half of it, that means theta, is the new orientation for your maximum shear stress plane. Let us solve an example. A stress state is given. Sigma x, sigma y, and tau xy is given. So we have to determine the principal stresses and the maximum shear stresses and their orientations. Well, first let's calculate the position, the location of the center of the Morse circle, and that is the radius of the Morse circle. You have those, that's your location of the center, that's minus 15, okay, and the radius is 69. Number 1, principal stresses. Well, the principal stresses are here, sigma 1 and sigma 2. How do we calculate? This is R minus this value, the center. R minus this value gives you sigma 1. And look at sigma 2. R plus this value gives you the sigma 2. So we can determine sigma 1 and sigma 2, location of the center plus minus r, minus 15 plus minus 69. Sigma 1 is 54, sigma 2 is minus 84. Now I have the principal stresses. The next is to determine their angles and their orientation. So this is my reference point A. So the angle between my reference plane A and the principal plane 2 is 2 theta 2. So take this triangle. In this triangle, when you write tangent 2 theta 2, so what can you say? That is 25. This is the coordinate of point A, 25. And that was 80. 80 minus 15. 80 minus 15 gives you tangent 2 theta. 2 theta 2 is 21. Theta 2 is 10.5. So I know which angle. I know the angle 2 theta 2. So for sigma 1, to find the orientation, I have to add 180 plus 25, that makes 201 divided by 2, that is an angle 100.5. So Having the values and having the angles, I can draw the new element. So this X and Y is my reference plane. And so when you rotate by 100.5, or you find what you find is sigma 2. When you rotate by 100.5, you find sigma 1. When you rotate 10.5, you find sigma 2. Well, these are my new, let's say, orientations, and we know that on these planes, I have the maximum and minimum stress. That means my principal stress values. Well, when you come to maximum shear stress, I have to find the minimum is here, maximum is here. Well, know that the tau max is equal to 69. That's the radius, which we have already calculated, and the center is minus 15, as we already discussed. Try to find the angles. I know that 2 theta 2 is 21. So to reach the minimum, I have to rotate the negative direction, and this is 90 minus 21. That's this angle. Its direction is negative, and that's 2 theta, and this is theta. And in order to find maximum, this is my reference plane. I have to move this way, and that is, as you see, 21 plus 90, 111, half of it, 55.5. Okay, that's my reference point. So in order to reach the maximum, I move in which direction? In this direction, in this direction, 55. In order to reach the minimum, I have to move in this direction. How much? 34. So these are the planes where on this plane I have maximum, on this plane I have minimum shear stress, and the angles are already calculated as we did. A simple problem. For a point, the stress rate is given. It's two-dimensional case. Determine the maximum in plane shear stresses and their orientations. First, we write down the components, sigma x, sigma y, and tau xy. And in order to construct the circle, the first thing we do is to calculate the average. That's the location of the center. That's 35. And 35 is here. And we have the center. And R is 81. And 81, we draw our MOHR'S circle. We check that our point minus 20, 60 is also on the circle. Yes, it is on the circle. The maximum in plane shear stress is in point E over here. Well, its value is, well, the radius of the MOHR'S circle. That is 81.4. And the sigma on the surface is the sigma average. So for point E, the components are 35 and 81.4. Okay, the next step is I have to determine the orientation of this plane. It means that I need the angle between my reference plane, that's point A, and E, that's 2 theta, I can use this triangle. So this angle is 2 theta and tangent of it is 20 plus 35 divided by 60 by this length gives you 2 theta, and you can find that theta is 21.3. Okay, drawing the element. So that was our reference plane. And when you rotate by 21.3 in this direction, you reach a plane where the shear stress is maximum and where the normal stress corresponds to the average normal stress 35. Well, another example. Here we have a rod. On this rod, a tension and torsion is applied. So as you see, the axial force is 900 newtons and the torque is 2.5 Newton meter. So diameter is given, find principal stresses at a point on the surface. What we do is, for a point on the surface, we calculate the stresses. We know the torsion formula. Tau equals to torque times radius divided by the polar moment of inertia. So on the surface, I have a shear stress 198. And due to the axial force divided by the area, I have a tension 716 kilopascals. These are the acting stresses on the surface, and this corresponds to the element. 716 normal, 179, 98, is the shear. So the question is, find principles. For this case, I have to draw first the Mohr circle. For the Mohr circle, that's the location of the center, average stress, radius of the circle. So determine the center and draw the radius, and I get my Mohr circle. I can check whether these 2 points are on the circle or not. Well, let us check first. Well, this plane has sigma equals to 0 and tau equals to 100. Okay, this is this point. And this point is somewhere over here. Okay, so you see this is a valid Mohr circle and I can work on it. What was the question? Question was the principal stresses. Well, not too complicated. Point D and point B are representing my principal stresses. What I have to do is, for point B, this is the maximum value. Finding this value is location of the center plus R, and finding the minimum value, location of the center minus R. You see, location of the center plus R gives you sigma 1. Location of the center minus R gives you the sigma 2 stress. Up to now, we have discussed the concept in 2 dimensions. In 3-dimensional case, so everything is the same. For a given stress state, you can determine your 3 principal stresses, sigma 1, sigma 2, and sigma 3. Well, the indices are given 1, 2, 3, starting with the maximum stress. You can not just name them as you want. So if your stresses are 10, minus 20, and 0, well, 10 is your sigma 1, 0 is your sigma 2, and minus 20 is your sigma 3. Well, the Mohs circle for this case is shown. You see 1, 2, 3 are your principal stresses. The in-plane stress conditions, two-dimensional cases, which we have considered up to now, can be seen as a three-dimensional case, but a special three-dimensional case where one of the principal stresses is 0. Let's solve a last problem. Due to the applied loading, the element at the point of the frame is subjected to the stress state shown. Find the principal and absolute maximum shear stress at this point. So we have a frame, loads are acting, and due to these loadings, a stress state like this is created and principles are solved. So for this case, if you take this plane as A, well, your sigma is minus 20, your tau is minus 40, and on the other perpendicular plane, sigma is 0, so the center is minus 20 plus 0 divided by 2, and that gives you minus 10. That's your center, and you can calculate the radius as this value, and it's 41. You can draw the Mohr circle. Center is by minus 10 and the radius is 41. Well, the question is find the principal and the absolute maximum shear stress. The principal stresses are where the circle intersects with the x-axis. That's the minimum and that's the maximum. These values you can find with the help of the location of the center and the radius. So this point has a sigma, as you see, minus 10 plus 45, that's 31.2. And this distance is radius plus 10. These are both negative. It's minus 51. Okay, so we have the principal stresses in the plane. The next is to find the angle. Well, that is my reference plane. So in order to find this angle, that's the angle from the reference plane to the minimum principal stress plane. So what you have to do is to find this 2 theta, you have to build the tangent. Well, this is 40 divided by this value, that's 20 minus 10. And do this calculation, you find that the theta value is 38. So this is my reference plane. You rotate in this direction by 38 and you reach a plane. Which plane? You reach the plane with the minimum principal stress, and its value is minus 51, as you see, minus 51 compression. So when you move another 180 or 90 on the element, you reach this point. This is the maximum principal stress in the plane. So that value is, as you see, 31. So what about the maximum shear stress? We know that it corresponds to this point. And in this point, the maximum shear stress equals to the radius, so tau max is 41, and in this point the sigma value is the average normal stress. That's the location of the center. There you have minus 10. The same problem we can also discuss in 3 dimensions. We have found that in the plane we have considered the principal maximum is 31, the principal minimum is 51. But when we consider the 3rd dimension, that is the direction out of the screen, perpendicular to the screen, there the stress is 0. I have another principal stress which is 0. So if I do name according to the rule these stresses, my sigma 1 is 31, my sigma 3 is 51, and my sigma 2 will be 0. Well, this type of notation is very important, especially in applying failure criteria, which we will deal later. You can also draw the 3-dimensional Mohr circle. You have your sigma 1, sigma 2, sigma 3, and we will not go into detail of these 3-dimensional circles, and that will be the end of our Mohr circle video. In this video, we have discussed a very powerful graphical tool for stress transformation and solved some problems. Thank you for listening.